Okay, so next I would like to look at resonance effects. And these do involve the charged atom, but they can also, clearly they're also involving neighboring atoms as well. So resonance will stabilize any charge, be it a plus or a minus. And it's a very powerful effect, and it works by delocalizing the charge. And that simply means instead of the charge being forced to be on one atom, the charge is shared out over multiple atoms. For example, if we look at acetic acid versus ethanol, we have an OH in here, and very often with acids, if we have the choice in an organic molecule of a CH or an OH, it's pretty much always going to be the OH that is the acidic position, or maybe an NH if we have an NH or an SH. So in this case, we need to look at the conjugate base forms. These are uncharged acids. So if we look now at these structures, we can see this one has the potential to do the type 4 resonance. This one has no chance to do resonance. These are sp3 carbons that are all singly bonded, no charges on them, so uncharged sp3 carbons cannot be involved in resonance. So let's see what we get when we do the resonance here. And let me write, these are the conjugate base. This one here can do resonance to form this other resonance form. This is going to stabilize this conjugate base. So if we have the more stable conjugate base, I'd like to ask my student actually, if I have two conjugate bases, this is the less stable conjugate base, this is the more stable conjugate base, which one is going to form more easily? The more stable conjugate base or the less stable one?
The more stable one.
Okay, so the more stable conjugate base forms more easily. So which acid is going to react first then? The acetic acid or the ethanol?
The acetic acid.
So which is the stronger acid?
Acetic acid.
Acetic acid, thank you. So, okay, so I'd also like to look at the possibility of acetic acid acting as a base. And we're looking now at this acid form where we've actually added an H plus to acetic acid. In the previous example, we looked at removing an H plus from it. But it is possible for us to have receiving an H plus, and compare that with this example with ethanol, where we've also protonated, added an H plus to the oxygen. Now, I do accept these aren't quite so equivalent, because here I've put the H plus on this oxygen, here I've put it on the top one, but you'll see the reason why I've done that, because this one, again, like the earlier example, cannot do any resonance. So the acid form can do no resonance. And ethanol is simply the conjugate base of this acid. But this one, as long as I put the H plus onto this oxygen, now I can do some, well, I could actually do some type 3 resonance, but I'm going to just focus on the type 4 resonance, which is going to be the main type. And if you want the arrows for that, that's how it goes. So again, the acetic acid version can do resonance. We have lone pairs on the oxygen, we have sp2s on the carbonyl, so we have this set of 3. This is going to do type 4 resonance, and actually that's wrong. It should be a resonance arrow. It's not an equilibrium, it's simply resonance. This is the equilibrium going on between the acid and base form. And so which is going to be more stable, the one that can do resonance or the one that cannot do resonance?
The one that can do resonance.
Okay, so this is the more stable form than this. So if it's a more stable acid, is it a weaker acid or a stronger acid?
Stronger.
No.
Weaker.
If it's more stable, it's going to be less likely to donate an H+. And if it's less likely to donate an H+, that means it's weaker as an acid. Now we have this effect then that acetic acid here is acting as a base. So not only is it acting as a base, acetic acid ends up being a stronger base than ethanol. And that's because it's forming a conjugate acid which is more stable. So curious thing that acetic acid is a stronger base than a simple alcohol. Okay, so finally we have to consider the inductive effect. And this is an effect of electron withdrawing or electron donation, which is not due to atoms bearing the charge, but atoms near those bearing the charge. So if we take our friend acetic acid again, and this time we're treating it as an acid, and we get forming its conjugate base here. It can do resonance as before. But this time I'm comparing it with trifluoroacetic acid. And that can do exactly the same reaction. It can donate an H+ from here, form the conjugate base, and then that can also do resonance. So we're no longer in the situation where one does resonance, the other doesn't. So the only difference here is not in the charged atom, it's the same, and in fact in both resonance forms it's sp2 oxygen, sp3 oxygen with a minus, and they switch the charges. These are identical. But way over here, 2 or 3 bonds away, we have some fluorines. And those aren't bearing the charge, but fluorine is very electronegative. It's the most electronegative element in the periodic table. And so if we have 3 of these all on 1 carbon, that's going to tend to be pulling charge towards it. And that means anything that has a negative charge is going to be stabilized through this inductive effect. And so that means that this conjugate base is more stable than the one from acetic acid. So remember, if our charged form is a more stable conjugate acid, that means, if our charged form is a more stable conjugate base, then we can say the corresponding acid is a stronger acid. And the acetic acid that forms a less stable conjugate base, that means it will be less likely to form. So this is a weaker acid. Now, in fact, this is roughly pKa around 5. This is roughly pKa around 0. So this is, in fact, 100,000 times stronger acid, roughly, than acetic acid. And this is really close to being, it pretty much is a strong acid under the classical definition, meaning it's almost totally dissociated in water. So those are the main factors affecting acid strength. We have the various effects on the atoms bearing the charge. We have the effects of resonance, and we also have effects on the inductive effect, where we have nearby atoms. These are also based on electronegativity, but in this case, it's electronegativity of nearby atoms. And don't forget, you always want to look at the charge form to assess stability. And if that charge form is a more stable conjugate base, then the corresponding acid is a stronger, less stable acid. If the charged form is an acid, then if it's the less stable form, that will be the stronger acid. The weaker acid, if you have a charged acid, the weaker acid is going to be the one that's stabilized through resonance or whatever is the factor.